Okay, the final lesson in the unit on electricity and magnetism is the motor principle. So what's our learning goal for today? I can explain the motor principle and use it to predict resulting characteristics that occur in the real world. Okay, so I want you to be able to use right-hand rule number 3 because that's the one that's related to the motor principle, and I want you to be able to apply it. So what is the motor principle? Again, something you don't have to regurgitate. So the motor principle states that when two magnetic fields interact, they produce a force. If a current carrying conductor cuts through a uniform magnetic field, so how about we kind of do the diagram at the same time I'm doing the explanation so you can kind of decode what's going on here. So the motor principle states that when two magnetic fields interact, they produce a force. So if a current carrying conductor, okay, so a current carrying conductor is a straight wire field. So let's put that one in. And for argument's sake, let's put a solid dot going with our convention. So that means that it's going into the page. Okay, so you take your thumb, you stick it into the monitor. So that would tell me that my magnetic field that's occurring here is a circular pattern like that. So that's the first one. So a current carrying conductor is that picture right there. When we put it through a uniform magnetic field, so what's a uniform magnetic field? Well, a uniform magnetic field is, I'll do these lines in blue. This is what a uniform magnetic field would look like. And I'm just picking down arbitrarily. How would you create that? Well, just build the magnet around it. So we have a C magnet. So the C magnet would create a uniform magnetic field with our north and south accordingly. Okay, so there we are. Now, next part. Sorry, I went blank there for a second, which is not uncommon. So, through a uniform magnetic field. So if it goes through at 90 degrees to each other, all right, so they're going to, basically the wire is going to be inserted in there. I'm going to draw my C magnet over here. So it's going to look like that. All right. And then I'm going to draw the wire passing through inside, like that. So now we have magnetic fields interacting. So I'll keep the color scheme the same. So we are going to have a circular magnetic field like this. And if you remember, we talked about this a little bit with field lines, they can't actually cross each other. So that means that the uniform magnetic field from the C magnet has to actually bend around to get to the other side. So that they do not actually touch, or they cannot touch actually. So that means they got to bend around. So you got to kind of squish the lines a little bit and make them curve so that they work. Here we go. So that's what's going to look like inside that magnet. So that straight wire conductor kind of bends the uniform field around it. Now, the force. That's what we want to know, is what this results in a force. So the strength of force depends on the strength of the uniform field and the field around the conductor. Okay, so anyway, how do we know what the force is going to be? I'll come back to this slide in one sec to add that in. Right-hand rule number 3. This is the one that's going to tell us. So what you need to do is you need to open your right hand so that your fingers point in the direction of the uniform magnetic field. So, for argument's sake, try to draw your right hand as best you can. So mine kind of looks like this. I hit my thumb the other night, so it's a little bit larger. And all my fingers are the same length, which is really cool. Alright, so basically I open my right hand. The fingers are going to point in the direction of the magnetic field. So my heel is at the north, and my fingertips are going to be at the south. And your uniform magnetic field lines are going to go in this direction. So I'm kind of building it around my right hand. All right. So what you would do is once you figure out the direction of the uniform magnetic field, you put your fingertips towards south. Now you need to rotate your hand until the thumb points in the direction of conventional current. So again, I'm building it around this situation. So if current is heading in that direction, that's the direction my thumb is going to go. And what happens is that the force produced, and this is the last line, the orientation of the palm indicates direction of force. So it is going to be perpendicular to your palm. So that would mean that I need to draw a force going this direction that's perpendicular to my red line and also perpendicular to my blue line. So my resulting force is perpendicular to my palm. Okay, so if we go back a page to the previous example, what's going to happen here then, just move this up so we can see it a little bit better. So here, my thumb, I'm going to point it inside into the page, and my fingers have to dangle downward, all right, in the direction of uniform flow. So your fingers, your hand doesn't have to be parallel to the monitor. It can be turned sideways, because if I have to put my thumb going into the page, my fingers are going to be dangling downward. But that's fine. They don't have to go in the direction of the magnet. It's as long as they're pointing down. My palm then is pointing to your left. So the resulting magnetic force will look like that. Okay, so it's perpendicular to my palm. Okay, and if you need some help with that spatially next day, there's no problem. Okay, we'll get it straightened out. So, application of electromagnet, kind of finishing up a couple of things here. So what would an electromagnet look like in a scrapyard? So basically what they do with the electromagnet is that they get a big hunk of soft iron. And they weld a couple pieces of soft iron to that soft iron. Okay, what they then do, and I'm going to use red for my wiring system here, what they'll do is they'll have a switch, and they'll have some form of power source. Not too worried about, we'll make it a battery even though it's not a battery. What they'll do then is they're going to coil the wire around, oops, so close. All right, I got to wrap it the right direction. So they wrap it around the one soft piece of iron here, and to make sure I do this right. So I want to make sure when I electrify this, the current, I'm going to assume current is in this direction. Okay, so that would mean my fingertips would have to wrap, because it's coming up and over. My thumb would be pointing downward. So this piece of soft iron would become north. This would become south. Because it's in contact, the larger piece of iron would become a north pole here for the magnet. As the wire runs across the other pole, we have to be careful because we have to wire it the other direction. So I think it would go over top and then connect back to the battery. The circuit, just double checking. So now my current is going up and behind, so that would be where my fingers point. So now this becomes north, this could become south, which makes the large piece of soft iron south. So now it creates a large magnet. All right, so I'll just put 0.1 here, connecting the circuit. Results in the given dipoles. All right, just make a bit of a note here. These two are wired differently, okay? Wired different. And that's what gives you the north and south. You got to be very careful on the direction of coil here, okay? Secondly, as soon as power is cut, nothing remains magnetic. All right, so as soon as you cut the power, all the stuff that's magnetic there with north and south dipoles are done. Okay, the poles would become neutral again, and whatever is being attached to that soft iron would be dropped. Okay, so that's all it is. They're just throwing a switch in the cab of the machine that's turning the power on and off to the magnet. The more juice that's hooked up to the crane, the stronger that magnet would be able to lift more material. But as soon as it's cut, it just drops off. So that's how a steel scrapyard magnet would work in all applications. And basically the question that I ask you either in the lab or on the test is related to this concept. So you just gotta, so I'm gonna put here concept will be on test, just as a heads up. So basically I'm not gonna put the scrapyard magnet on the test, but it's gonna be something that's related to it. Okay, so moving along here now. Faraday's law of electromagnetic induction. So then Faraday came along after Ørsted, and he came up with his law, and it states that a magnetic field that is moving or charged in intensity near a conductor causes or induces electron flow in the conductor. So what does that basically mean? Well, it means this. If I have electric current over here in this box, Ørsted, let's see if I can make it decent arrow. Ørsted said if you have electric current, then you can create magnetic fields. So what did Faraday say then? Well, Faraday said, hey, if we take Ørsted's the other direction, if I have a magnetic field, I can create electric current. And that's basically the relationship. So he took it one step further. So and I'm going to show you how that works with magnetic fields, because in order to create that magnetic field, we need Lenz's law. So Lenz's law simply states that the direction of induced current creates an induced magnetic field that opposes the motion of the inducing magnetic field. Now, to me, it's like anything else. It sounds like double talk. I need to see an example. So here's Lenz's law, quite simply put. So basically, if you were to pass this magnet, and through the magic and miracle of science here, I can take my magnet here, and what I'm going to do is I have basically a soft iron core. Okay, so soft iron, and I got coil wire, and nothing's magnetic. What Lenz said was, if I take this magnet here and I go and pass it over top, I can go on all day like this, pass it over top, what's happening is that I am going to be able to induce the flow of electrons. Okay, so that means that north-south then becomes north-south. All right, and I'm forcing, or I am inducing electrons to flow, which means that if that becomes north and south, if it aligns the same as that particular magnet, it means that my flow, using conventional, will flow in here using your right hand rule number 2. So your thumb would point to north, it's going to go over the wire, it's going to exit here. So flow is induced. Electron flow is induced. Okay. If I take that same magnet and go the opposite direction with it, so I'm not flipping the magnet around, you'll notice the north and south line up. So what happens if I go the other direction with it? So I spin it this way. Alright, so I'm just passing it over top. I again will induce current flow. The difference is the north and south end would be reversed. North and south is reversed, which means I can reverse the current flow. Okay, this is how your generators work. So I'll cut it off at that point, and we'll finish the note on the next video.